Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Chris White with us today. Hi, Chris.
Hello.
How are you today?
Doing well, I guess.
Where are you at?
Well, I'm in my home, but right now I'm a postdoc at the KITP in Santa Barbara.
Okay.
But I will be transitioning actually to a joint position, a postdoc position between Princeton and the Flatiron Institute in a couple months. So,
Oh, that's fantastic. Congratulations.
thank you.
That is very awesome. And has UC Santa Barbara Cobley Institute, have they opened up yet, or are things still shut down there?
No, things are still pretty shut down, and it's also still dealing with cleaning up after a water main break next to my office. So
yeah, I saw pictures of that actually. Yeah. Oh, that was next to your office. Oh, lovely.
Yes.
So did they get your office rebuilt or reconstructed?
Yeah, I think it's all been rebuilt from the ground up. It almost seems, but.
Oh wow. Okay. Nice. So Chris, what do you like to do for research?
Well, I guess, have two things, which is fluid dynamics and black holes, and especially where the two of them come together. So mostly I do kind of computational simulations of accretion onto black holes, maybe some other compact objects. And I guess, these days there's a lot that you can connect with, recent observations of black hole accretion. So it's kind of an exciting field.
Yep, it's definitely a hot topic these days. So speaking of, let's go ahead and take a look at one of those hot topics today by looking at this really lovely paper. And I'm going to share my screen. And this one is on the effects of tilt on the images of black hole accretion flows. And Chris, take us away.
Yeah, so this is one of those papers where, for a while I've been thinking about tilted disks, which is to say, black holes have spin, and the spin might very well be misaligned with the kind of general angular momentum of the stuff falling into them. And that misalignment can lead to all sorts of interesting dynamics. And then, along came the Event Horizon Telescope observations.
Right.
That was just last year, right? And
right.
So they showed M87, and I was looking at all the results, and I was like, this is great, but one thing that hasn't been studied yet is what if the gas falling onto M87 is not aligned with the spin of the black hole? Mm-hmm. And quite understandably, I mean, that's extra parameters you don't need in your first crack at the data, right? But I was, kind of thinking, well, we have seen in the past that, there are qualitative differences to the accretion flow if the black hole is spinning rapidly enough and it's misaligned enough with the infalling material. But what we hadn't asked until we saw the EHT data is, what would this look like to the EHT? Mm-hmm. And so this paper is kind of a first stab at, exploring, what sort of signatures might we actually expect to see? There's two ways you might be able to dismiss tilted accretion flows, right? Either they're not distinguishable from aligned ones, in which case there's no point in looking at them, or they would be so completely different that we would just take one look at the M87 data and say, well, it can't be tilted, and then we could also dismiss it. Right. This paper was trying to see, are either of those the cases, or is it kind of the interesting regime in between where there are differences, but they're not so obvious that you can just dismiss tilted disks out of hand? So that's.
Let me ask I don't know, so let me just ask the question. Are there similar things in like protoplanetary disks or accretion disks in regular binary star systems?
So I would imagine, yes. I mean, for different physics, basically you sure. need some way to get kind of a quadrupole moment in the mass. And so here we have, the spinning black hole, but if you had a companion star, you could also induce interesting dynamics. Okay. Yeah, unfortunately, before everything was kind of shut down, I was going to go to a conference all about kind of dynamics, this sort of interesting dynamics in disks that are everything from protoplanetary to black holes.
Perfect.
So I'd also like to know more about other regimes here.
Yeah, I just threw that out there. I didn't mean to derail you. So okay, back to it.
Yeah. So here the premise is very simple. We didn't want to do like let's reanalyze the entire EHT data set with extra parameters, all just the four of us. That would have been a lot. But we decided, I had these two simulations, one where angular momentum of the material was aligned with the black hole, and another where it was inclined, and just compare A versus B. What did the images look like in an EHT context?
Cool.
So I don't know if we scroll down. So figure one is just a simple, this is a kind of a mid-plane slice of the density. The only thing to really grab here, it's very hard to visualize these non-axisymmetric systems. I've looked at 3D plots I've tried to make, and I can never get anything that shows what I want. But in a 2D slice, I think in the bottom panel, there's the tilted simulation. You can see there's large density contrasts. These are both on the same color scale. You get these kind of non-axisymmetric standing waves in the disk. Whereas, there's transient non-axisymmetric stuff in the top panel in the aligned case, but it's nothing very strong. And so there's what I'm talking about. Qualitative difference is the accretion flow axisymmetric or not? And you would expect, if you introduce these strong non-axisymmetric features, that should probably have some impact on what you see if you get a resolved image. So
is the central black hole here? Is this a sink, or do you?
Oh yeah, sorry. Yes, I should say the
or what?
Yeah, so this is in the Kerr metric. This is a full GR MHD simulation.
Okay.
So I think it's not numerical relativity, and that the disk is basically massless and not gravitating, but all the GR effects of the black hole are in there.
Okay.
And I think that's kind of important for capturing the effects we're looking for here. So we are really focused on just a few gravitational radii away from the black hole, what's going on there.
Okay. Cool.
So yeah, there's some description here of just the numerical setup. But then I think, yeah, figure two here is kind of, now this is showing what the sort of simulated data products are that we're working with. So I should say we're using Athena++ to do the hydro simulations, and then GR Trans, Jason Dexter's code, as he's the second author there, and his code is one of these ones that you can ray trace through simulation data to model what happens with the synchrotron emission and absorption from the plasma, including all of the GR effects for bending the light rays near the black hole, and also capturing things like polarization as well. So you basically we take a snapshot from our simulation and turn it into just an image on the sky. And this case, so you have to specify just a few parameters. What's the actual mass of the black hole, because in the simulation it doesn't matter. It's a scale-free sort of thing. You specify the mass of the black hole. You specify the scale of the density in the simulation. You decide where to place your camera relative to everything, and then you get a picture. And this is kind of illustrating, we took the mass of Sagittarius A star, which conveniently enough, we don't presently know the orientation of its spin, if it has a spin at all. So we're free to kind of just say what it is, just for probing the differences in these simulations. And so here I'm kind of looking straight down the spin axis, and in the top, when we're kind of looking down on the disk of material, it's more or less axisymmetric. There's some transient stuff in there. Whereas on the bottom, there's consistently brighter and darker parts of the images, and there's this non-axisymmetric spiral swooping in toward the middle of the image. So you don't get this kind of nice circular hole in the image. And this is just kind of showing that, here's a 0th order thing you expect to see differences between aligned and tilted images. Of course, we can make these very pretty ray tracing images, but at the moment we're limited to the size of the Earth in terms of how good our resolution is for this interferometry, the EHT. So you don't see something quite this detailed. So then you have to, what we do is just a simple kind of convolve it with the effective beam width that the EHT has. And so you get a much more blurred image. And then I guess our question kind of evolves into, given the current resolution of observations, can you still see a difference between aligned and tilted disks? So I think maybe one of the next figures might have it's blurring.
Remark on this figure that
oh yeah,
gets pretty hot, a few times 10 to the 10.
Yes, that's the brightness temperature, which I guess is, I mean, yes, the plasma is very hot when it's fallen that far down in the potential well.
Right. So any material that was there is been put into its nuclear statistical equilibrium state. Yes. Guaranteed. Anyway, that's another topic.
Yeah. So I work a lot alongside people doing stars and other things, and they'll talk about a hot star is a few 10,000 Kelvin or something. I'm like, oh, that seems pretty cool to me.
Relatively, yes. Okay, so here's our blurred beam, or our
yeah. So here's what happens after we blurred that kind of sharp image, and I'm just showing the 5 panels across are just 5 different snapshots in time. So you do get time variability in these things. And so the question is there a systematic difference between the top row and the bottom row? That's what we're generally asking.
And got it. I understand. Yep. So this is a time sequence of images.
Right.
Mm-hmm.
And so, here we looked at it, and immediately just by eye, we were like, well, the shadow in the center of the image is quite circular in all of the top cases, but actually rather elliptical in the bottom cases.
Mm-hmm.
That was and again, this first case was, what if Sagittarius A star is a face-on disk, which we started with just because I think it's the easiest case to see differences in.
Sure.
And so the next figure is just quantifying this by tracing. We have an algorithm for just tracing out what are the ridge lines of this, the boundaries of this image, so just so we can actually put numbers to it later on. Cool. But the end result is, yeah, if we were lucky enough to have the simple case when we look at the galactic center, that the black hole spin is pointed right at us, we could probably easily tell whether or not the stuff falling into it is tilted or not.
Okay.
But again, that was just a simple case. So I think if we go down to
so here we're doing this looks like time averaged.
Yeah. So this is, I mean, the trick with, of course, the galactic center is the gravitational time is 20 seconds for that black hole. So we expect stuff to change on that time scale. So if you take an observation that lasts a better part of a day, you're going to get some very time averaged appearance. So this is what happens if we time average over similar length of time in our simulation, and we see kind of still this difference between a circular shadow and an elliptical shadow in the center.
Mm-hmm.
And I think it's also important that we're looking at this because you'll see, how do you get elliptical shadows? I mean, there's other ways you might imagine some sort of modification to general relativity. And I think one of our points here is that, well, before you start modifying GR, there's complicated, all the plasma physics of all this stuff circling the black hole can also lead to all these interesting effects as well. I think if we scroll down to the next kind of images. So here's a more generic case where the black hole spin is not pointed straight at us. It's 45 degrees off the line of sight.
Okay.
And the disk is either aligned with that or just at some other angle as well. So here, nothing's axisymmetric in the image, and you get kind of interesting effects all around. So the left is just the high resolution version of this, and the right is kind of, well, now we blurred it again to sort of imitate the EHT resolution at the moment. So here we have the more difficult question is there a systematic difference between the top and the bottom? If observations, when the EHT observations come through. So I'm not a member of EHT. I don't know what the status of that is, but I do know, they have data on the galactic center, and soon, hopefully, they'll, really have some release of that data. And the question is, could we compare it and say, does it look like the top or the bottom or something like that?
Right. Right.
And so I think here you get this crescent shape in both of them. But our thoughts were, there are still differences in terms of, is the crescent symmetric between its top and bottom halves? And also there's still a shadow that tends to be more circular in the top case and more elliptical when the accretion flow is misaligned with the black hole.
Yes.
So I think it's kind of really interesting that, despite the fact that we had to blur out all the beautiful detail on the left, there still are some, first order effects that come through that allow you to say something about the differences here. I guess if we go down the third case, this is more just quantifying what I just said. If we go, the third case is now we shift focus to M87, where there actually has been a release of data. And here we have I guess you can say it's a benefit that we kind of know the direction of the jet coming out of M87 relative to our line of sight. So we could align, say, in this case, the spin of the black hole with that. We know how everything's oriented on the sky. So I guess it gives us less freedom to just change the camera parameters to show whatever we want. And so here, kind of satisfyingly, when we align everything the way we think it should be aligned, we get roughly what the EHT sees, which is kind of this crescent in the bottom half of the image. But again, here's high resolution. There's kind of, in the tilted case, there's this stream that kind of spirals in toward the middle of the image, whereas in the top case, it's a rather evacuated black hole shadow.
Right.
And I guess, yeah, go ahead.
That's okay. I'm with you. I'm good.
Yeah, so I guess if we go down, here again, we blur it and get very EHT-like images. And again, there's, depending on when you take your snapshot, it could look a bit different.
Right.
But again, the question is there a difference between the top and the bottom panels? And here, actually, I think one of the differences that kind of struck us by eye and that we wanted to then quantify is, in the top panels, you get just this one central bright spot. In the bottom panels, you tend to get this kind of clumpiness going on. I think actually, if you scroll down, oh yeah.
Those are your ring contours underneath the plot.
Yeah, so there's those contours, but I think it's figure 14 or 15, yeah, 14 here. So this just shows, like, if we walk along kind of the ridge line in that blurred image and just record the brightness, on the top, in the aligned case, we did it for 20 or so different snapshots, and you get this very monomodal thing. There's a bright point and it just gets dimmer away from that. If you walk along the ridge line of that ring in the tilted case, you kind of always get 2 or 3 peaks in the brightness. So it's there's a qualitative difference that you would think would, you could incorporate that into your models. Now, of course, the caveat is, we took the data and we just blurred it with the Gaussian, but in practice, what you're really doing with the EHT is you have this kind of, you're poorly sampling the Fourier space when you're making this interferometry measurement. And it's entirely possible for there to be, a perfectly smooth thing on the sky that when you back out an image from this your data, it'll just look clumpy as well. That's just an instrumental artifact from interferometry. So if you look at the the M87 images that were released last year, there are 2 or 3 bright spots, and we're not saying, well, here it is, it must be a tilted disk, just because it has a couple of clumps in it, but it's showing that something that could be there could be kind of an artifact of the way the nature of the data could also be something that's telling us something physical about the source. So you'd want, I think, in the future, one thing we're kind of pushing for is folding in the possibility of tilted accretion flows into kind of the full data analysis, and then you can at least statistically say, is it likely that this thing is tilted, or is it likely that this is all instrumental or something like that?
And I just want to correct something I said. I didn't quite realize what was being plotted. So that's actually the brightness temperature.
Yes, sorry.
So just correcting what I said earlier. Okay, very good. Cool. And that.
Yeah, so that was.
So what were some of your conclusions you got out of this?
Yeah, so I think our conclusions were we are in that interesting middle regime where you kind of tilted. If you have a tilted disk, it's entirely possible that it looks qualitatively different from an aligned one, but not so much so that you can just take one look at it and say, oh, it's this or that. It's kind of you want to do a proper analysis, which, well, I think it's interesting, but it's also kind of hard because if you're comparing to a library of simulation models, adding in the extra parameter or two that covers tilts, that makes things expensive.
Yeah. So where do we go from here? Would it be worthwhile doing another 20 3D simulations? Should we wait till the next EHT images? Where does sort of this work in the community go in this regard?
Yeah, so I think one direction is, here in this kind of first take on these sort of effects, we're very focused on just the image plane and how that appears in brightness temperature. But there's other parts of the data. So you can look at the spectrum over, everywhere from the millimeter to the infrared. And we already have data for, say, M87. What does that spectrum look like?
Okay.
And we've actually started to look at that, where we realize the spectral slope will change depending on whether the disk is tilted or not. But it's degenerate with some other stuff that we still have to sort out. You can also look at polarization, right? That's EHT naturally should be getting that. So again, this is data that exists but has not yet been published. So I don't know what it'll look like, but we have the capability to kind of investigate, are there polarization signatures in this? So before we have to do another 20 massive simulations, we could do just a little bit more analysis of the simulations we have. But I think also a big thing will be, what will the data actually look like? What really spurred this project on was seeing the EHT data and saying, okay, now we know this is what I can do to my simulation to kind of match it to the observations. So kind of when something comes out with polarization on Dell, I think I'll have a clearer idea of, okay, this is how you connect theory to observations with polarization. Or when they release the galactic center data, then it's, okay, this is what the galactic center looks like, and this is probably all the caveats we need to know about, time-dependent interferometry, and all of that has been sorted out.
Cool. So just out of curiosity, how long does it take to do one of those simulations? Whatever metric you want to use.
Yeah, I'm trying to think. I mean, order of magnitude, like 1 million CPU hours, something like that. And I mean, if you give me more time, I will use it just as.
Of course. like telescope time. That's awesome. Well, cool. Seems like there's the future is bright. On this topic, and there's certainly lots of stuff to do, and it's a hot topic now, and I don't think it's going to be going away anytime particularly soon. So as more data comes in, as more simulations come in, it'll be really interesting to see how things play out over the next 5 years or so.
Indeed.
Cool. Chris, I want to thank you so much for sharing your lovely paper with us today.
All right. Thank you.
And everyone, thank you so much, and we will see you on the next one. All righty. Bye-bye.